Hello, my name is Jacob. Welcome back to the Introduction to Sane video series. In this example, we will show you how fun and easy it is to simulate unbalanced AC power flow in Sane. Let's start by opening our network. This network is adapted from the IEEE 123 bus distribution system, which has been laid out over Brattleboro, Vermont. We also included a synthetic sub-transmission network to connect it to the ENET39 network, the network used in our other Intro to Sane videos. If we zoom in, we can see where our sub-transmission system is connected to our distribution network. Just as we did in our Intro to AC Power Flow video, let's briefly look at the line properties of this model. Recall, AC power flow simulations only require positive sequence property values. To execute unbalanced AC power flow simulations, we specify zero sequence property values as well. We have configured this network to use per length values so that the line length property can be used for scaling. We can set our branch legend to view the number of phases across our network. After selecting one of our single phase lines, we can confirm its exact phase with the property editor. If we come to our Model Explorer, we can see this distribution system has been configured with 17 solar generators. Let's investigate how those generators operate during a peak demand day scenario. Viewers familiar with the ENET39 network from our other Intro to Sane videos will notice that the peak demand week scenario dates are the same across the two models. In fact, all the profiles can be shared between the two models. In a later video series, we will show you how these models can be seamlessly integrated for generation and distribution analysis. Recall from the other videos how quick it is to view results using the chart window. Clicking on the IEEE 123 distribution zone, we can see the demand and generation on this feeder only. As expected, we noticed the peak solar generation occurs in the middle of the day. However, our solar isn't able to cover all the demand on this feeder. So, looking back at our sub-transmission connection point, this is a line that connects the IEEE 123 feeder to our sub-transmission system. This plot confirms our expected behavior. We see that as the solar generators ramp up, our active power supplied by the sub-transmission system dips, but then slowly increases as demand grows. This top plot gives us some insight into what is happening on each phase. We've also included a custom script to show the loading on each phase at the feeder head, along with the neutral current. From this plot, we can see that the phases are not equally loaded, as can be seen by the non-zero neutral current. Let's look at the voltages in our system. But I want to look at the voltages right after this spike in loading at 4 p.m. By changing the branch legend to show the phase A voltage magnitude, we can see that our phase voltages range from 0.989 to 1.058. Note that the phase B and C lines are blacked out. Using my command window, I can mark all of my nodes whose phase A voltage is below some value, let's say 0.99 pu. It looks like we have a series of such nodes in the middle of our network. So what would happen if we increase the power capacity of any solar generators near these nodes? Let's find out. I'll start by selecting all the solar generators on the map. And it does look like a nearby node has a solar generator. Let me select that solar generator using the node bar and set its new default maximum active power output to be 0.5 megawatts. I will rerun our scenario. I need to make sure that I come back to that 4 p.m. hour of interest. Let me grab that query I ran before. After running it, I can see those nodes are no longer below 0.99 PU, which is expected due to the local generation coming from the solar generator. For those viewers interested in other methods to remedy voltage problems, we encourage you to investigate the impacts of placing a shunt near these loads. In this video, we distinguish the properties needed for unbalanced power flow from those needed for balanced power flow, executed an unbalanced AC power flow scenario, investigated a simple method to assess the voltage impacts of distributed solar. Thank you for watching our video on unbalanced AC power flow simulation. Hey there, just a reminder to check the video description for links to helpful resources like the model used in this video, other instructional videos, documentation, and our Saint user forum.